Hello, and welcome to another section of Physics in My Pajamas, or PIMP. Doing some pimping here, we're going to talk about an introduction to momentum. So we're going to go ahead and start by thinking about something we looked at, the exact same situation we looked at last unit. When we were starting to talk about energy, we said, well, I know that there's a type of energy that deals with motion. We call it kinetic energy. And we said, if I wanted to change the kinetic energy of something, say, for example, maybe there was an eraser sitting in the chalk rail, and we said, well, gosh, if I wanted to change the momentum of that thing, then I would need to go ahead and exert some force on it, wouldn't I? Because we said F is ma, and we said if I want to change the kinetic energy, that energy of motion, I would have to accelerate it. And so I would need to have some force that would accelerate it. And we said, gosh, it doesn't just matter, though, we said, how hard I push. We also cared about the length of the push, we said. We said we cared about that displacement, or that distance, rather, through which we pushed. In fact, we said, if I went ahead and I did a calculation like that, and we said, if I look at that force dotted with the displacement, we said that went ahead and gave us something that we gave a name to. We called it the work done. And we said that work that's done, if I add up the work done by all the forces acting on a system, then that gives me the change in the kinetic energy of the system, right? And so we could use this calculation for work to figure out how much the energy of the system was changed by. But at the same time as we did that, we said, well, yeah, I'm also going to change the motion of this object, not just by pushing through a distance. Instead of talking about the length, that length I push through, we could talk about the length of time that I apply that force. The more time that we push through, the bigger the change in the motion is going to be. So we're going to look at the same situation, but in a slightly different way. We said we're going to go ahead and talk about it not in terms of the distance we push through, but in this unit, we're going to talk about it in terms of the duration that we push through. Okay, so that time that we push through. And so we would say, I could talk about that time. I could use a t, or I could use a delta t, which might make it a little bit clearer that I'm not talking about a clock reading here. I'm talking about a duration, a length of time that force is applied. So what we're going to do is we're going to say, hey, this force times the duration of the push. We say that's going to give us a new quantity. All right. And when we do that, in fact, we're going to go ahead and use, at least for today, I'm going to use the symbol J, capital J for that. All right. And you say, hey, that force through a duration, the actual name we're going to give that, we're going to call that the impulse. You say, well, when we applied a force through a distance over here, we did work, and that work changed the kinetic energy. Well, now if I go ahead and I do a calculation, same situation, but I look at it in terms of force and duration, I'm going to cause an impulse, and that impulse, is going to change something different. Instead of changing the kinetic energy of the system, it's going to change the momentum of the system. So if I were to add up all of the impulses done to the system, that would equal to the change in the momentum. Now, the symbol for momentum is going to be a lowercase p. Okay? And so we're going to change the momentum of the system when we apply an impulse. And you say, well, gosh, to figure out what this momentum thing is, let's go ahead and do a little calculation. Now, we did a calculation when we did the work calculation. I don't know if you remember, but we said we could, using this idea that work is a force through a distance, we said we could calculate a formula using this. We could calculate a formula for that kinetic energy. You'd say, well, gosh, this force through a distance, it's changing something. What is the thing that it is changing? Okay, so that change in kinetic energy is going to be equal to the work that's done. And you say, well, that work that's done, I can say, we'll use the formula, most important formula in physics, and that is F equals ma. And so I'll substitute in ma for F, and you say that delta x, then we still have hanging around. You see now where it says A, I'm going to go ahead and use a good motion formula to substitute in. We knew that kinetic energy had something to do with motion, with velocities, and we said, hey, let's rewrite acceleration in terms of changes in velocity. And we said, well, gosh, we also would love to use this delta x in there since we have that. And so we said, hey, we'll use the formula v squared is v naught squared plus 2a delta x. Rearranging that, we would have gotten that my acceleration is v squared minus v naught squared over 2 delta x. Substituting that in for a, okay, and we still have that that m hanging around, right? And we still have that delta x hanging around. And you say, well, now, right, this is equal to that change in kinetic energy. And by the way, when we calculate a delta, that's always going to be the final minus the initial, isn't it? Okay, that's how we calculate a change in kinetic energy. All right, good enough. Just bring that down. And if I continue on with this, you say, well, gosh, when we did this, hey, this delta x here and this delta x there canceled each other out. And if I go ahead and distribute that half and the m, we wind up getting this. Look, we got a 1/2 m v squared minus a 1/2 m v naught squared. We say, hey, look, what's this thing that I'm changing when I do this work and I apply this force through a distance? You say, well, it changes this 1/2 mv squared thing. We said, hey, that's our formula for kinetic energy. Kinetic energies are 1/2 the mass times the speed squared. And we said, hey, that's what a work changes. It changes the kinetic energy or the energy of the system. Coming over here, we'd like to do something similar for impulse. And so you say, well, an impulse, that's going to change this momentum thing, our delta P, right? And we say that's going to be equal to my impulse that's done on the system forced through some time. You say, okay, well, we'll go ahead and say we'll do the same sort of substitutions we did before. We said, when I apply a force, okay, I say I could substitute in my equation, most important formula in physics, F equals ma. If I substitute that in, I'm going to have ma times my duration. You can feel free to change there for me. Really? Okay, whatever. Times my duration. And where it says A, we're going to go ahead and substitute in a kinematics formula like we did before. You say, well, this time, again, I'm thinking about the change in the motion of this object, so I want to think about velocities, but this time I've got a delta t to get rid of, so I'm going to use a different kinematics equation. I'm going to use V is AT plus V naught. Rearranging that, A would be equal to V minus V naught over T. Okay, or if you'd like, we're talking about the duration between when it was at V naught and when it's at V. So again, we can kind of think of that as being a delta T. If I go ahead and substitute that in, you see I'm going to get a V minus V naught over delta T. Okay, we still have that mass hanging around. And we still have that delta T, but not for long. Because say, hey, that delta T, you say, isn't that going to cancel here? And you say over here on the left side, this was the change in momentum. You say, well, change in momentum, wouldn't that be final momentum minus an initial momentum? That's how you do a delta, a final minus initial. You say, hey, what is this P thing we're changing? Well, look at this. If I distribute that M, isn't that going to be mv minus mv naught? You say, well, that's my momentum minus my initial momentum. You say, hey, what is the formula for momentum? Isn't the formula for momentum, isn't that going to be just P is mv? That is what the formula is for momentum. All right, derived using kinematics, F equals ma, and our force acting through a duration. It changes this P thing, which is equal to the mass times the velocity. All right, and so that's it. That's our formula for momentum. So what is this momentum thing that we're changing when we apply a force through a duration, when we apply an impulse? Okay, what that momentum thing is. Let's see here. Let's give a nice formal definition here. So you say this new thing. this new quantity, this new thing that we can calculate. We're going to call it momentum. We're going to use the symbol lowercase p for it. Okay, again, we're not going to use a capital P because capital P is for power, as we learned last unit. So you say, hey, what is momentum? Well, Newton defined this as the amount of motion. You might be wondering, hey, if this is momentum and it's the amount of motion, what letter would you tend to think we would use as a variable to represent it? Well, wouldn't you think we'd use an M? Well, we can't use an M, though, because we're already using M for mass. In fact, it's in the momentum formula. It would be really confusing to have M as MV. So we're going to use a P. You see, well, still, of all the letters in the alphabet, why are we using P for momentum? And that's because this P actually stands for the Latin verb pater, okay, which is Latin for to move. Okay, and momentum is the amount of motion. And so it's from the Latin verb. And you say, in fact, this is not new to you. You say, hey, we saw this before in the word centripetal. We said, hey, that came from pater. Again, centripetal, of course, meant towards the center or moving towards the center moving, strictly translated. And so he said, so that's, so again, we're using this again for the amount of motion. And if you think about it, you say, hey, this formula, the amount of motion, it of course should depend on how fast it's going. The amount of motion should depend on that velocity there. And it should also depend on how much stuff is moving, right? The more things that are moving, the more motion we have. You say, well, gosh, mass, if I had, same object, but just twice as much of it, wouldn't there be twice as many particles moving? I'd have twice as much motion. So, yeah. So it makes sense that it should also depend on mass. Okay, and of course, P is momentum. Hey, you know what, though? Something that I am going to point out right away. I'll tell you something special about this formula. When we did kinetic energy before, we came out that kinetic energy was 1/2 the mass times the speed squared, right? Yeah. That V was speed. Something I want to warn you about just right off, and that is in the momentum formula, this V is specifically velocity, not speed. In other words, this V is a vector. It's an arrow. It has a direction. Sometimes in math, they'll use this little symbol over things that are vectors. You say, now, mass isn't a vector. It's a scalar. Mass doesn't have direction. But you say, well, gosh, this side of the equation, the right side, has to equal the left side. And this right side has a direction, so the left side has a direction. That is to say, momentum is a vector. This is really, really important. In fact, the most common mistake in this unit is forgetting that these things have directions, and we have to be really, really careful about that. When I do a problem, I like to set up my little coordinate axes and assign, I'm going to call that way the positive direction. Well, I better make sure that my signs on my V's and my P's are correct. Not only that, if I want to change the momentum of a system, we just figured out that that's going to require an impulse, which is a force through a duration. You see, when I look at this equation, if my momentum has a direction, the change in momentum, that change in P, that also has a direction, doesn't it? I might be gaining momentum to the right or gaining momentum to the left, right? So that momentum has a direction. And so I could think about this delta P as being a vector, and the force has a direction. Hey, when you have an equation and something, the left side has a direction and the right side has a direction, how do those directions compare? Well, that's right, they've got to be the same. The direction that you push in, that's the direction that the impulse is in. Remember this whole chunk here, force times the duration, that's called the impulse. Okay, that's impulse. Impulse has a direction. That's the direction the force is in. That's also the direction the momentum changes by. If I push to the right, the momentum it gains momentum to the right. If I push to the left, it gains momentum to the left. So my momentum, my P, my velocity, my v, my change of momentum, my delta p, and my force, my f, and my impulse, my j. These are all vectors that all have directions. And we got to be really careful about pluses and minuses in our calculations for those. You will see that much more in the next video. But for now, this is where we're leaving off. Almost forgot. You know what we should talk about? We should, while we're here, talk about units. You say, hey, what are the units for this thing? You say, well, mass would be in units of kilograms, and velocity, of course, would be in meters per second. And so you say, well, gosh, that means the unit for momentum is going to be kilogram meters per second. And you say, well, gosh, that seems kind of long to say, oh, I have a momentum of 15 kilogram meters per second. That seems kind of long. Is there a way to shorten that up? And the answer, not really. They did not invent a special unit for momentum. The unit is just going to be kilogram meters per second. However, over here, you say, look, if my momentum is in kilogram meters per second, my change in momentum ought to be in kilogram meters per second, right? Oh, I had 5 kilogram meters per second, and then I lost 2 of them, so my change was minus 2 kilogram meters per second, perhaps. You say, but on the right side, you say force would be in newtons, and time would be in seconds. You say, wait, is a newton second the same thing as a kilogram meter per second? Well, just to make sure, you say, I remember that force is equal to ma, mass times acceleration. So if I had a force in newtons, a newton must be the same thing as mass in kilograms, acceleration in meters per second squared. So a newton is a kilogram meter per second squared. And I'm going to take that, I'm going to multiply it by seconds. That the second here on top is going to cancel that square on the bottom. And what am I going to get? Kilogram meters per second. So a newton second is the same thing as a kilogram meter per second. So these units are technically interchangeable. We usually see newton seconds used for impulses and kilogram meters per second used for momenta and changes in momenta, but they really do calculate out to be the same thing. I think that'll do it for the first little intro. But what I would say is recognize that besides that formula saying that momentum is P is m times V, the other thing that's really important here is, hey, in the energy unit, what was the central formula for that unit? Wasn't it this idea here? Work is the change in the energy. This was the big energy balance equation. Later on, we could tack on other kinds of energy, delta U, U's, and so on. You see, but this was the big formula for energy. That was the central formula that we could plug in formulas for work and the different kinds of kinetic energy, do our calculations for our conservation of energy equations. Well, over here, likewise, this is going to be the big central formula for momentum. But this sigma j thing, j for impulse, it's very rare that I see people use that symbol j. So instead, we're just going to go ahead and substitute directly in the formula for impulse, force through time. So sigma force through time, that's our impulse, is equal to the change in the momentum. This is going to be the central formula for this unit. It's just, for whatever reason, people don't tend to use the symbol J for impulse very much. They almost always just immediately plug in F delta T. I think it may just be that we're so used to always working with forces that they just automatically start plugging that in. But for whatever reason, this J symbol doesn't get used too much. People usually just go directly to F delta T. So much so that sometimes students forget that F delta T is for impulse. And like they get asked to calculate an impulse, and they're like, I don't remember what's impulse again. They start looking for something labeled I. No. Force through duration is the impulse. So that's it. So this here is going to be the big central formula for this unit that we'll be plugging into for all our calculations. This is like the starting point of our calculation. Look at all the outside forces on my system. Define my system, look at all the outside forces, multiply the durations. That gives us the impulses that will change the system's momentum. I think that is where we'll end this video. And I'll pick up next time by taking a look at the way that momentum is conserved. That's it.